Okay, so what we are talking about your acceleration of a container in the liquid. We are filling the liquid in a container, and the container is right now moving with a certain acceleration in the upward direction. If I need to calculate the pressure at your point of your A, then as it is open to the atmosphere beta, as this vessel is open to the atmosphere, so atmospheric pressure is acting in the downward direction, weight of the body is also acting in the downward direction, and as the body is moving in upward direction, so I can see here right now, so if I'm writing the equation, you see, we'll get a clarity. So weight of this liquid is acting in the downward direction beta, mg, and atmospheric pressure is also acting in the downward direction, and along with that one, pseudo force is also acting in the downward direction, m into your A, that is nothing but equal to your pseudo force. So that is the reason we are getting the pressure will be equal to P naught plus H rho into your G plus A. Now, if the container is moving down with an acceleration A beta, here the weight of the body is moving in the downward direction. Atmospheric pressure is no doubt in the downward direction, but pseudo force is in the upward direction. Pseudo force is equals to your m into your A in the upward direction. So pressure in this case will be written by P is equals to your P naught plus of your H rho into your G minus of your E. Clear, beta? Moving in the upward direction, positive. Moving in the downward direction, it will be your negative. Any doubt to anyone in this one? Sure. Next one. If the liquid is moving in the horizontal direction, okay, there is a wheels for this one like this, and this one is accelerating in the front direction. Initially, liquid is being filled in this one up to this level. The moment it starts moving with an acceleration A, the pseudo force starts acting on that body beta. And because of the pseudo force, the liquid will try to move in the downward direction. So level of the liquid will become something like this. Okay, and it will start making a small angle with this given condition. So this is making an angle of your theta. Got it? Now tell me what all the forces will be acting on this body. One is no doubt weight of the body acts in the downward direction beta, m into your G. Pseudo force acts on this body in this direction. That is nothing but m into your A. Resultant of these two forces, the resultant of these two forces are acting on this body. So that will be equal to your, it is your m into your G effect. Clear? Clear, beta? Okay. So m into G effective will give me what, beta? M into your G effective will be equal to your angle between them is 90 degrees. So it is under root of your, this one is your mg into your whole square plus of your m into your A into your whole square. Isn't it? So this will become for me m into your G effective is equals to, this one is under root of your, this one is m square into G square plus m square into your A square. Okay, so if I simplify this one further, I'm writing somewhere here, you see. So it will be your m into your G effective is equals to your root of your m is, this is your m under root of your G square plus of your A square. M and m gets cancelled. So G effective is equal to how much, beta? G effective will be equal to under root of your G square plus of your A square. So this is your G effective. G effective is equals to your under root of your G square plus A square. Clear, beta? So these are the three cases you should remember in the static condition. If it is moving in the upward direction, P is equals to P naught plus H rho into G plus A. If it is moving in the downward direction, P is equals to P naught plus H rho into G minus A. If it is accelerating in the front direction, then G effective is equals to under root of G square plus of your A square. Clear, beta? Then how do you write the angle made by this one, beta? So if I'm taking an angle right now, so this one will be your theta. So tan theta will be equal to your, tan theta will be equal to, I'm writing just here, tan theta will be equal to your. Can you tell me, beta, how do you write the tan theta value? Anyone? What is the value of tan theta? Which side by which side? See, if this is your MA, this side is also your MA beta. Okay, and this side is also your MG, like this. Okay, so that will be equal to how much for me? M into your A divided by M into your G. MM gets cancelled. So tan theta will be equal to your A by G. So this is your angle made by this one. So tan theta is equals to your A by G. Okay, very good. So these are the three formulas you need to remember for the acceleration of the container with a certain liquid. Clear, beta? Any doubt in this one to anyone? Clear? Clear, beta? Any doubt to anyone in this one? Sure. Next one. Fluid dynamics. I'll do the statics problems also better once we complete the basic concepts. Buoyancy concepts, floating condition problems, but all problems I'll do separately. Okay. In fluid dynamics better. The things you need to remember in the fluid dynamics is what do you mean by a streamline flow and what do you mean by a turbulent flow? What do you mean by streamline flow, beta? What do you mean by a streamline flow? Streamline flow. Streamline flow is nothing but, like say for example, if the water is been flowing like this, if it each and every point the velocity is same, isn't it? That is known as of your streamline flow. So here it is V, here it is V, and here it is V. The streamline may also be in the curved path beta. Here the velocities, if I am taking like this, here the velocity might be your V1. Here the velocity might be your V2. Directions are different, but velocities will be the same. Clear, beta? It may be a curved path or it may be a straight line, streamline flow. Okay. So the path traveled by a fluid particle is called as a streamline. It may be a straight line or it may be a curved path. If I draw a tangent at any point on a streamline, that gives me the direction of the flow beta. Tangent drawn on your streamline will always gives me the direction of velocity of your flow. You can write that one. Tangent drawn on streamline, on your streamline gives direction. Streamline gives direction. Clear, beta? Okay. Another name for the streamline flow is, it is also called as of your laminar flow, or also called as of your steady flow, or also called as what? Steady flow. These are the different names for this one. The next one is about your turbulent flow. Turbulent flow. Turbulent flow is nothing but the flow in which the velocity of the liquid is not same, or I can say it is your unsteady. It is your unsteady. Okay, that means at a given cross section, velocity of the fluid will be varying with the time taken. Okay, so velocity changes with respect to time. velocity changes with respect to time. Such type of your flow is called as of your turbulent flow. Clear, beta? Streamline flow, the velocity of the fluid doesn't change with respect to your time. So I'll write that one with the another pen, we get a clarity. So in this one, velocity of fluid doesn't change with the time. Doesn't change with time. If it is changing with respect to time, that is called as of your turbulent flow. Clear? Third one is critical velocity. Third one is critical velocity. Did anyone remember the critical velocity beta? The velocity at which the fluid is being converting from laminar to turbulent is called as of your critical velocity, represented by your VC, isn't it? So the velocity of fluid, the velocity of your fluid, which is converting from laminar to, from your laminar to turbulent. Laminar to turbulent is called critical velocity. Is called critical velocity. So that critical velocity will depend upon, critical velocity is directly proportional to your coefficient of viscosity of liquid, directly proportional to the diameter of the pipe, and inversely proportional to your density. Critical velocity is directly proportional to the coefficient of viscosity, inversely proportional to the diameter of the tube, and inversely proportional to the density. So what is your neta beta? Neta is nothing but your coefficient of viscosity. Coefficient of viscosity. And capital D is your diameter of your pipe or tube. And rho is nothing but density of liquid. Density of your liquid. Clear, beta? Removing the proportionality constant, I can write Vc is equals to some constant R into neta divided by capital D into your rho. So critical velocity is equals to your R into neta divided by capital D into your rho, where rho is density of liquid. And what is this constant is known as, beta? This constant capital R is known as of your Reynolds number. Very important for the NEET theoretical question, beta. Reynolds number here. So how do you calculate the Reynolds number? Capital R is equals to your critical velocity, diameter of the tube, into your density of your liquid divided by your coefficient of viscosity. That will give me the Reynolds number. Clear? Now see, in this one, if I'm writing some points which are really very important. First one, if 0 is lesser than R and R is lesser than of your 0, that means the flow is laminar. The flow is laminar, or also called as of your streamline. Okay, the same way, if R is greater than 2000, then flow is turbulent. If the value of the R, if I'm getting greater than 2000, that will be your turbulent. If 1000 is lesser than R and R is lesser than your 2000, then flow is changing from laminar to turbulent. Laminar to turbulent, which is called as of your critical or unsteady state, or your unsteady state or critical state. These values are very important, beta. Lesser than 0, the flow is a laminar or streamline. Greater than 2000, no doubt it is a turbulent. The value between 0 to 2000, when it is converting from laminar to turbulent, that is called as of your unsteady or critical value. Clear, beta? Is that clear? So next, an important formula in this one which you should remember is equation of continuity. Equation of continuity. So what is an equation of your continuity, beta? It is based upon your law of conservation of your mass. It is based on law of conservation of mass. That means whatever the liquid is entering at one end, the same amount of the liquid will be coming out. Like say this is your tube. So this is your area of cross section A1, and here the area of cross section is A2. And here the velocity of liquid is V1, and here the velocity of liquid is V2. Okay. Now if I'm saying that if certain amount of liquid is entering into this pipe, whatever is the entering liquid, the same will be your outgoing liquid. So I can say that incoming liquid will be equal to your outgoing liquid, isn't it? Like say if 1 liter of liquid is entering at A1, same 1 liter of a liquid will be going out at your A2. So there is no change in mass. So that is the reason we are writing it as of your law of conservation of your masses. So equation of continuity is based on what, beta? Law of conservation of your masses. What is the formula? And not deriving the formula for this one, beta, because it is of no use right now. You can directly write the relation. It is your A1 V1 is equals to your A2 into your V2. V1 and V2 are your velocities. A1 and A2 are your area. So V1 and V1 is equals to V1 and V2 are velocities. Okay, and A1 and A2 are your area of your cross section. Clear? So rate is nothing but what, beta? Rate of flow. Rate of flow. Anything divided by time is known as rate. That means volume divided by your time is known as rate. That is V by T. So rate is represented by Q. Q is equals to your V by T. That is nothing but A into V, which is nothing but constant. So rate of flow of a liquid in this container is always remaining for me constant. That is AV is equals to your constant. Clear for everyone? Any doubt in this one to anyone? Any doubt, beta? Any doubt in this one to anyone? Now tell me whose area is more, beta, in this one? A1 is lesser than A2. A1 is lesser than A2. Clear? If A1 is lesser than A2, then V1 will be greater than V2. Lesser the area, more will be the velocity. If area is given in terms of radius, if A is equals to pi into your R square. So I can write here A1 V1 is equals to your A2 into your V2. A is equals to pi into your R1 square into V1 is equals to pi into your R2 square into your V2. Pi and pi gets cancelled, so it is your R1 square into V1 is equals to your R2 square into your V2. This will be your answer. Clear, beta? Is that clear? Any doubt in this one to anyone? So what is an equation of continuity, beta? Equation of continuity says that whatever the liquid has been entering at one end, the same amount of the liquid will be leaving the other end. So A1 V1 is equals to A2 V2. If area is not given, but if area is given in terms of radius, like circle or square or rectangle, you can take the area of that one and substitute in the place of A1 and A2 by definition. Okay. So next one, Bernoulli's theorem. Bernoulli's theorem. So what is the Bernoulli's theorem, beta? It is based upon your law of conservation of energy. Based on law of conservation of energy. Okay. So liquid possesses what type of energy, beta? It possesses kinetic energy, it possesses pressure energy, and it possesses your potential energy. So if I'm writing the definition for this one, it states that the sum of your pressure energy, comma, kinetic energy, comma, potential energy at any point in the path of streamline, in the path of your streamline. Okay, per unit volume or per unit mass is constant. Okay, so what is the Bernoulli theorem? It states that the sum of your pressure energy, it says that the sum of your pressure energy means PV, and kinetic energy means half mv square, potential energy is mgh at any point in the path of your streamline flow per unit volume or per your unit mass is always constant. Okay, so I'm just writing first the energy beta. Pressure energy is your P into V plus kinetic energy is half into M into your V square plus potential energy is your mg into your h. That will be equal to your constant. This is your actual formula. So PV is place of your half mv square plus of your mg into your h is equals to constant. First one, this is known as total energy beta. This total is known as of your total energy. So this total energy per your unit mass, first one, unit mass or unit volume, sorry. Unit volume. That means PV divided by V plus half into M into your V square divided by your V plus of your mg into your h divided by your V must be equal to your constant. Isn't it? So this V and this V will get cancelled. So it is your P plus mass by volume is nothing but density. So it is half into rho into your V square plus mass by volume is density rho g into your h will be equal to constant. Isn't it? This is your another form. Second one. Total energy per your unit mass. That means P into V divided by your M plus half into M into your V square divided by your M plus mg into h divided by your M. That will be equal to your constant. Isn't it? So V by M will be equal to how much beta? Density, because density is equal to mass by volume. So I can write this one as P divided by rho plus this M gets cancelled, V square divided by 2 plus this M will get cancelled. So G into your H is equals to your constant. So this is your another form of your formula. Okay, so these are three different forms of your Bernoulli theorem. So Bernoulli theorem is based on law of conservation of energy, which says that the sum of your pressure energy, kinetic energy, and pressure energy at any point in the path of a streamline flow per unit volume or per your unit mass is always remaining constant. So these are three formulas you need to remember in this one. I'm not going for the proof of this one better, so please try to remember relations. Clear for everyone? Is that clear? Sure. One more form better. This one, if I am multiplying with your G, right here, right now itself. So this is a P divided by rho into G plus V square divided by 2 into G plus G and G will get cancelled. So that will be equal to your H, will be equal to your constant. Like this also I can write, right? This one is known as of your pressure head beta. This one is known as of your pressure head. Pressure head is nothing but P by your rho G. And the dimensions of that one are equal to height beta. V square by rho G is known as velocity head. This one is known as of your velocity head. Okay, and this H is known as gravitational head. Gravitational head. Clear beta? P by rho G is known as of your pressure head. V square by 2G is known as of your velocity head. And H is known as of your gravitational head. And dimensions of all of this one will be equal to what, beta? Height. The dimensions of all these three will be equal to your height. Okay. All heads, I'll write here. All heads has dimensions of height. Very important. Clear, beta? Sure. Next, let us try to go for your applications of this one. Applications of Bernoulli's theorem. Bernoulli's theorem. Application of your Bernoulli's theorem. Bernoulli's theorem, I'm also writing it as of your B. Done? It's the first one. For horizontal pipes. For horizontal pipe. Okay, let's see. There's a pipe like this. This is a point A and this is your point B. And there is a liquid in this one like this. Okay. Now see, if I take any point on this one beta, which are in the streamline, like say if I'm taking 1 point here, 1 point here, 1 point here, 1 point here, all of them will be in the straight line. That means this is your reference. This one is your reference. And at reference, the potential energy is always 0 beta. At reference, the potential energy is always taken as of your 0. Okay. So now, if I'm talking about the point at A, and if I'm talking about your point at your B. So for horizontal, A and B are at the same height beta, isn't it? As A and B are at the same height, so I'm applying the Bernoulli's theorem at point A and point B. I'm writing here, you see, Bernoulli's theorem at your A must be equal to Bernoulli's theorem at your point B. At point A, let's say for example, if it is moving with the velocity, this liquid is moving with velocity V1, and here this liquid is moving with velocity V2. So I can write here, pressure here is say for example of your P1, and pressure here is say for example of your P2. So this one will be P1 plus of your half into rho into your V1 square plus rho G into your H is equals to, this one is pressure P2 plus of your half into rho into your V2 square plus of your rho G into your H. This one and this one will get cancelled right now from this one, isn't it? So pressures as they are at the same point right now, isn't it? So what I can write the relation right now beta from this one, as a point P1 and P2 we are taking, both of them are in the same straight line. So this P and this P, whatever is incoming pressure, the outgoing pressure is also your same. Clear beta? So where the pressure will be more beta? Wherever the larger area, pressure will be the more. Okay, so you can keep 1 point here. Large area, pressure will be more. Velocity will be less. Velocity will be less. And lesser area, pressure will be less. Pressure will be less. Velocity will be maximum. Velocity will be maximum. Okay, that means I can say right now here P1 is greater than P2 and V2 is greater than V1. Clear? Is that clear? In this point, P1 is greater than of your P2. Clear beta? Very important relation. And whatever liquid is entering, the same liquid is also coming out beta. That means here I can write A1 V1 is also equal to your A2 into your V2. This equation also you can use. This is my equation number 1. and this is my equation number 2. So by using these two relations, we can calculate or we can solve the numerical. Clear, beta? Sure. So for horizontal pipe, the heights will be the same. So it is P1 plus half rho into V1 square will be equal to, that means if I'm simplifying this one, so I'll be getting this one as of your P1 plus half into rho into your V1 square is equals to your P2 plus half into rho into your V2 square. So P1 is greater than, so it is P1 minus of your P2 will be equal to your half into rho common V2 square minus of your V1 square. So this is your pressure difference. Clear? So next one. Dynamic lift. Dynamic lift. Aeroplanes, if you might have been seen, they will be moving in the air. The wings of this one is something like this. The air will pass from this one like this, and the air will pass from this one like this. Okay. Now, if I'm taking 2 points here, beta, here 1 point and here 1 point. Listen it carefully. So this here, at this position, the velocity is V1. At this position, the velocity will be V2. So obviously, as if the plane is moving in the upward direction, V1 must be greater than V2. Then only it will move in the upward direction. Now, if I'm taking the pressure here as P1 and pressure here as of your P2, whose pressure will be more, beta? P2 must be greater than P1 because it lower side, the liquid is more or the air molecules are more. So that is pushing the body to move in the upward direction. So it is moving in the upward direction. So that means at point B and at point A, at point B, the pressure will be the more. So P2 will be greater than P1. And at point A, the pressure will be the less. So V1 will be greater than V2. And pressure at P2 will be greater than of your P1. Clear for everyone? So now, because of this difference in this one, this will get lifted in the upward direction. So this one is force acting on this one. This force we are calling it as of your lifting force, FL. So what will be the lifting force, beta? Lifting force will be equal to your pressure difference into your area of cross section, because pressure is equals to force by area. Force is equals to pressure into area. That pressure is nothing but equal to how much, beta? P1 is greater or P2 is greater here, beta? P2 is greater right now, isn't it? So if I'm writing P2 is your greater right now, so I can write here right now, P2 is greater than P1. P2 is greater than P1. So I'll write here with another pen. As P2 is greater than P1, I can write your pressure difference P2 minus of your P1 is equals to same general formula, half into rho into velocity V1 will be greater. So it is V1 square minus of your V2 square. So therefore, dynamic lift will be equal to your P2 minus of P1 into your area of cross section. So this is the formula for your dynamic lift. P2 minus P1, you know, so limiting dynamic lift will be equal to your half into rho into your V1 square minus of V2 square into area of your cross section. So this is your dynamic lift formula for your aeroplanes. Clear, beta? Direct formula applications are being used in your doing of numericals. Any doubt in this one to anyone? Any doubt, beta? Okay. So in the first application for an horizontal pipe, same height gravity, heights will get cancelled, and depending upon that one, we got the pressure difference relation and also the dynamic lift relation. Clear? The next one, third application, beta. Pitted tube. Pitted tube. Can anyone tell me what is a pitted tube, beta? An instrument which is used to measure the speed of your river. Okay, a device a device which is used to measure the speed of water in the river is called your pitted tube. Here, beta. Like say, this is your river flow. Okay. Now in this one, we are having some L shape or type of your instrument like this. Okay, this is opening right now here. This will be the opening right now. So the moment you keep this one into the water right now, what is happening is water enters into this one. Now this water enters with a certain velocity. So this is the water which is been entering into this one. Then from here, it will try to rise in this tube up to a certain height. So up to somewhere this height, it is been rising. So outside the liquid, outside the river, it is H. And this height is, say, for example, of your H naught, to which it has been raised in the tube. Okay. Now, if I'm taking this one as of your reference point, beta. So this one is your reference. At reference, the potential energy is always taken as 0. So this is 0.1 and this one is your 0.2. Okay. So applying the Bernoulli's theorem at 0.1 is equals to Bernoulli's theorem at your 0.2. Streamline flow, isn't it? So now, when it is moving in inside, the velocity of this one is equals to your half into rho into your v square. Plus, it is open to the atmosphere because it is open right now atmosphere. This height from here to here will be equal to how much? Beta H naught. That is open to the atmosphere. It will be your P naught. So this will be your P naught plus of your H naught rho into your G. Okay. Plus reference of potential energy is 0. That will be equal to your open to the atmospheric pressure. So that will be equal to P naught plus. Now the liquid will come to a certain height and velocity will become for me 0. So it is half into rho into velocity will become for me 0 because it will rise to a certain height and stop there. Plus potential energy will be equal to how much, beta? H plus of your H naught into rho into G, because the height to which it has been total raised is this much height. Clear? So from this one, if I'm writing the relation, so this will become for me half into rho into V square plus this one is your P naught plus of your H naught rho into G. That is equals to your P naught plus H rho G plus of your H naught rho into G. Anything is getting cancelled in this one, beta? This P naught will get cancelled. H rho naught G will get cancelled. So it is half into rho into V square is equals to H into rho into G. This density also will get cancelled. V square is equals to 2G into your H. Our velocity V is equals to under root of 2G into your H. So this is the velocity of the river. What is the H, beta? Height of the liquid which is raised in the tube above the river. H value. See the diagram? That will give me the value of your V. For competitive examinations, directly see the why I have written the steps means to understand how do you do the numericals in the Bernoulli theorem. Whenever you are taking any 2 points, how I am applying the Bernoulli theorem at the 0.1 and 0.2, where I am taking velocity 0, why I am taking the velocity 0, how I am writing the pressure, that all things you need to do or you need to remember while doing the problems of your Bernoulli theorem part. So velocity here will be equal to how much for me? Under root of your 2G into your H. That means the device which is used to measure the speed of the water in the river is called as pitted tube, and that velocity is being, or that velocity of the river is being calculated by the formula V is equals to under root of your 2G into your H. Is that clear for everyone? Sure. One more application. Tap water. If you might have been seen the water coming from your tap, isn't it? So generally in the upper part, the water level will be more, and when it comes to the lower part, the level of the liquid will become slowly changed. Okay. So if I'm taking this one, there is water filled in this one completely like this. Okay. Area of cross section of this one is, say for example, A1, and this one is of your A2. And this is your point. The pressure here is say P1, and here the pressure is say for example P2. Whose pressure is more better? Obviously P1 is greater than P2. I told you larger area, larger pressure. Velocity will be equal to how much better? Here the velocity is say for example V1, and here the velocity is say for example V2. So obviously V2 will be greater than of your V1. So I can apply the equation of continuity beta. A1 V1 will be equal to your A2 into your V2, because whatever is incoming, outgoing will also be the same. Now apply the Bernoulli theorem at this point beta. So if I'm taking this reference right now, this one is your reference. This one is your reference. At the reference, potential energy will be equal to 0, isn't it? As it is open to the atmosphere beta. So this will be equal to P1 will be equal to P0, and P2 is also equal to P0. So I can write here P0 plus half into rho into your V1 square plus potential energy is 0. That is equals to your P0 plus, here it is your half into rho into your V2 square minus, with respect to reference, the height of this one is say for example H. H is below the reference, so it is a negative H rho into your G. This P0 will get cancelled, so it is your half rho into your V1 square is equals to your half rho into your V2 square minus H rho into your G. Clear? Now in the all those conditions, this row, and this row will get cancelled there better. So I'll be writing this one as V1 square divided by 2 is equals to your V2 square divided by 2 minus H into G. So I can write here V1 square is equals to V2 square minus 2G into H. That means I can write V2 square is equals to V1 square plus 2G into H. Isn't it? That means V2 will be equal to under root of your V1 square plus 2G into H. So the velocity of the liquid which has been coming out at the point of your P2 is given by the formula. V2 is equals to under root of your V1 square plus of your 2G into your H. That's right. Clear? If areas are being given, isn't it? And V2 is given, I can calculate the V1 from the given relations. I can use this equation 1 and this equation 2 to solve the numericals. Clear, beta? Is that clear for everyone? Clear? Sure. And for today's session, last one small topic beta. Then we'll try to go for the numericals application in the tomorrow. Torsilis theorem and velocity of Flex. Velocity of Flex. That means velocity with which the liquid is coming out through the orifice is known as of your velocity of your Flex. So this is your container beta. There is a small hole here right now. So from this one, the liquid is been coming out. And the liquid is being filled in this one up to this side. Okay. So this opening is called as of your orifice. Okay. So at this one, I'm taking the point 1. and this one I'm taking it as 0.2. This one is at a height of your h. Okay, here is your pressure P1, and here it is open to the atmosphere. From this one the liquid has been coming out, so this will be equal to your P0. And this one is your closed container, but not open. Okay, so at this one, see here, apply the Benelux theorem better, from where the liquid is going out. So this one I'm taking it as of your reference. At reference, the potential energy is taken as of your 0. Okay, so the reference, the potential energy is taken as of your 0. Done. Now apply the Benelux theorem better. 0.1 and 0.2. Applying the Bernoulli's theorem at 0.1 and 0.2. See here I'm writing again. Bernoulli's theorem at 1 must be equal to your Bernoulli's theorem at your 0.2. At 0.1 the pressure is P1. As the liquid is going very slowly, the velocity will be 0. Plus it will be rho g into h. From the reference, the height of this one is equal to h. That is equals to P2 is open to the atmosphere. From here the liquid is going out, that is rho into your v square. Why at P1 V1 is here taken as 0? Because the area of cross section is more. So more the area of cross section, lesser will be the velocity beta, isn't it? And at the reference, the potential energy is generally taken as of your 0. So it is 0 plus 0. So this will become for me P1 plus rho g into your h is equals to your P0 plus half into rho into your v square. So I can write here P1 minus of your P0 is equal to your, this will be equal to how much for me? All the P1 terms I'm taking on one side plus of your rho gh. This one is rho gh, rho g into your h is equals to your half into rho into your v square, isn't it? I need the velocity right now, beta. So I need the velocity from this one. So I can take this 2 on this side, beta. So if I'm taking this 2 on this side by deflation, so this will become for me how much, beta? 2 times of your P1 minus of your P0 plus 2 into rho g into your h is equals to your rho into your v square. Clear? This rho you take on this side, beta. So this will become for me 2 into your P1 minus of P0 divided by rho. Plus this one is 2 rho g into your h divided by rho is equals to v square, isn't it? So this row will get cancelled here. So velocity will become how much for me, beta? V square is equals to V square is equals to your, how much, beta? 2 into P1 minus of your P0 divided by your rho. Plus this will be equal to your 2g into your h. That means velocity v will be equal to your under root of your, this one is 2 into P1 minus of your P0 divided by rho plus 2g into your h. So this is the velocity formula, velocity of Flex. If container is opened, beta, if container is opened, that means P1 will be equal to P2. So in above formula, P1 is equals to your P2, then velocity will become how much for me? Under root of 2g into h. So this velocity is known as of your velocity of your Flex. Velocity of your Flex. Clear? So we'll try to do in detail applications or numericals based upon this one in the tomorrow session of a class. How to calculate the maximum ranges, how to calculate the time taken to empty the container, and blah blah conditions in the tomorrow session of your class. Okay, beta? Sure. Take care. Bye.